Good morning, Advanced Chemistry. Happy Friday, Snowfest. Yesterday we left off when the bell rang talking about KEQ and its definition. KEQ is set up to look like this. Just a reminder that those are your products raised to their coefficient powers. So C to its coefficient power and D. And if you had more products, you would include those as well, all multiplied together. And we're going to, in the denominator, have the reactants. And this expression here has a couple of names. It's called the mass action expression, which is sort of weird. And then it also is called the equilibrium constant expression, which I think makes a lot more sense. But either one of those two things, if you see those or read those in a question, it's referring to setting up this in order to determine KEQ. So it's the definition of KEQ, and it's determined by your actual reaction. So just a couple of things to say. All of these concentrations are at equilibrium. So you can't say this is the KEQ expression unless all of these concentrations are actually occurring at equilibrium when equilibrium has occurred, and they're constant and unchanging. If the reaction has not achieved equilibrium yet, or it's been disturbed out of equilibrium, then those are not valid. So it has to be at equilibrium. That's very important. So what I'd like to do now is to set up your expression for KEQ, your mass action expression or your equilibrium constant expression for the reaction that we were talking about yesterday, which, just to remind you, looked like this. It was 2SO2, and that was a gas, and that was reacting with O2, also a gas, and in irreversible conditions, product was 2SO3, also a gas. So our KEQ expression for this reaction, if we're going to say these have established an equilibrium, would be our product, SO3, and that would be raised to the second power since the coefficient is 2. And we would divide that by the concentration of SO2, and that would also be squared to the second power, and O2, which has a coefficient of 1, so it would be raised to the first power. And this would be my equilibrium expression, or my mass action expression for this particular reaction. And if we were to plug in those values of the SO3, the SO2, and the O2, and I can't remember what we wrote down for those on your graph, but at equilibrium, whatever we decided those numbers were, if we were to put those in, then we could actually find the value of KEQ. So there you go. This right here for this reaction is called a homogeneous equilibrium, because all reactants and products are in the same phase. And it happens to be a gas in this case. So that's called a homogeneous equilibrium. All gases, all reactants and products in the same phase. I'm going to throw something else at you here. Solids and liquids. If you have a solid or a liquid as a part of your overall equation, like up here in your A's, your B's, your C's, your D's, any product or reactant that is a solid or a liquid, we are not going to include those in the KEQ expression. So they just drop out, not factored in at all, because their concentrations are considered to be constant. So basically, that leaves only aqueous solutions and gases that are going to be included in the KEQ expression. Okay. So here's an example. It says write the equilibrium constant expression, remember that's one of those terms for finding our KEQ, for the following reaction. So I have a reversible reaction, and I have some sodium bicarbonate. Looks like it's decomposing into sodium carbonate, carbon dioxide gas, and water vapor. And what you have right here, if we find KEQ, is going to be called a heterogeneous equilibrium, as opposed to a homogeneous equilibrium, because you have different phases that exist. So you have solids and you have gases. So you have a heterogeneous equilibrium. So to set up my KEQ, I'm going to look at, well, first of all, make sure it's balanced, which it's not. So I'm going to need 2 NAs, it looks like over here. 2 H's, 2 H's, 2 C's. I'm going to need 2 C's there, it appears. And then 6 O's, so 4, 3, 7, 8, 6, 3. Why am I having so much trouble with this? Okay. Oh, because I have 2 C's already. Okay, I see. All right, so 2 C's, 1, 2 C's, 3, 5, 6 O's. All right, okay. So KEQ is going to be equal to, let's start with our products. Now this one's a solid, so that's not included in our equilibrium expression. Then we have CO2, which is, so I'm going to do the concentration of CO2, and it has a coefficient of 1, so it's just raised to the first power. Same thing for water. And remember, these would be the concentrations of those 2 species at equilibrium, and then we're going to divide it by our products, or excuse me, our reactants. These are our products. That balancing's got me all messed up. Our reactants, and the only reactant we have is a solid, so that's not going to be included in the expression. So essentially, that is our mass action or equilibrium constant expression. So there's no denominator, that's okay. Cool. Now what we're going to start to do at some point is find the KEQ value. So we'll do that now. Here I've got some dinitrogen tetroxide and making some nitrogen dioxide, and if we balance this one's a lot easier for me apparently. Here we have a homogeneous equilibrium happening. It says at 10 degrees Celsius, and remember, temperature has to stay the same for your KEQ to be constant. So this doesn't really affect our KEQ, it's just telling us that this is the temperature of interest. So at 10 degrees Celsius, a mixture in a 10-liter container contains 0.045 moles of N2O4 and 0.03 moles of NO2. What is KEQ? So this time we want to know what is the actual value of KEQ. So I'm going to move this off to the side. The first step here would be to find your mass action expression, or your equilibrium constant expression. So we're going to set that up first. Take our NO2 here as our product, and it will be raised to the second power. And we're going to divide that by the concentration of N2O4. And since everything's a gas, they're all going to be included in the equilibrium constant expression. So there's our KEQ. And now, and really this problem should say a mixture contains this at equilibrium. That's important. Remember, these 2 concentrations have to be at equilibrium in order to even be considered. So it's saying at equilibrium, you have a mixture in a 10-liter container with these number of moles. So what that's giving us is a way to do our concentration. So for our NO2, we have 0.03 moles divided by 10 liters. And we're going to square that quantity and divide it by, what's my N2O4? 0.045 moles per 10 liters. And that doesn't get squared. So now we can plug those values in, and 0.03 divided by 10 is 0.003, and we're going to square that, and that is 9 times 10 to the negative 6. So I'm going to write that down here, I guess. And that would be moles squared per liters squared. And we're going to divide that by 0.045. Divided by 10 is 0.0045. So we're going to just divide it by 4.5 times 10 to the negative third, and units there would just be moles per liter because it's not squared. And if you divide those two values, you're going to get 2. And really, if you look at sig figs, I guess we should just have 1. So it's going to be 2 times 10 to the negative third, I believe. Let me just double check that. 9e6. After I mess up my balancing, I just want to double check. And our units, moles squared divided by moles, are just going to be moles. Liters squared divided by liters are just going to be liters. So this is the value of KEQ. And you will notice that it's pretty small, 0.002. Units, as you can see, are kind of like K for rate. They're units of convenience, whatever they happen to end up being, based on your expression. Alright, let's talk about what KEQ tells us. Remember we were talking about the equilibrium position, and the equilibrium position was the relative amounts of products to reactants. So if you look at KEQ, and we look at the definition, back to our definition, if KEQ is large, i.e. if KEQ is bigger than the number 1, that tells us that the numerator, which represent our products, that factor ends up being a bigger number than your denominator. So your top numerator portion is bigger than your bottom number, which means you have essentially more products than you do reactants. So we're going to say, because you have more products, we're going to say products are favored at equilibrium. So you're going to have a bigger value up here. If your KEQ is less than 1, that means your reactants are favored at equilibrium, because these product numbers are going to be smaller, your denominator is going to be bigger. So that means your reactants. Now this might be a reaction that just doesn't go very well. You don't make a lot of products. That would be bad for things like industry where you're trying to make a lot of a certain product. So you want a very large KEQ, or as big as you could, if you were trying to make a lot of a certain product, like maybe some kind of a medicine or some kind of a consumer product. Okie dokie. So here is our last little sample problem here. It says, finding the value of KEQ. We already did one. I would like for you to do this one, so I'll ask for your substitute to pause it here, or if you're at home watching, pause the tape. And I want you to try this. It's just like the one we did. Finding the value of KEQ can be kind of easy or kind of difficult. We're going to just stop today with the easy, and then we'll get into the hard next week. But finding the value of KEQ when you're given all of the concentrations at equilibrium. So that would be just plugging in your values. So I'm going to have you stop, try this problem, and then you can go over the answers with me. Okay? In this case, we have a unitless number because we have moles squared per liter squared in both the top and the bottom, and that's okay. And the value of KEQ is large, which tells you that this reaction favors the products at equilibrium. Meaning, at equilibrium, we're going to have a proportion of this hydrogen iodide that is large, and if we were trying to make hydrogen iodide, that would be a good thing. So now you have some to practice on your own. I will tell you what those problems are. You can ignore this. Those problems are going to be found on page 601. And 601, you're going to do 1 and 2. 602, you're going to do 3 and 4. And 603, you're going to do 5 through 12. And I will look forward to seeing you on Tuesday. Enjoy your day off on Monday. But don't forget, you're going to have your LTA 3.3 on Tuesday when you return. No quiz that day. So have a lovely rest of your Friday. Enjoy your Snowfest weekend, and I will look forward to seeing you very soon. Have a wonderful day.